my, my apologies, I had no idea I was muted. Well, it's a great pleasure to be here today. It's also very hard to follow Andre and David talking about decision diagrams. So it's all downhill from here, but maybe you can see some different perspective. And I'm very hopeful that you can find some interesting problems here that you could try to improve, like where you could try to find a better solution than I found. So I'm going to talk to you about like the idea of finding decision diagrams when you're branching to solve discrete optimization problems, especially when you're trying to enumerate solutions. And if you want to do some sort of what we call post-optimality analysis, which is you have solved the optimization problem, but you're doing some what if type of analysis with the solution set. So all of this work was either co-authored or inspired by my PhD advisor, John Hooker. In one case, he's one of the authors of the paper. In the other case, he's not an author, but I would have never come across this problem or thought of these things if he didn't put it in front of me. So he's a person with the vision, and I just try to figure out a way to make it work. So with that said, I'm going to start talking about one of the things that bothers me a lot when I think about solving optimization problems, which is when we get to a point of enumerating possible solutions, especially if you're looking for more than an optimal solution, if you're trying to enumerate all the solutions of a problem, or at least the near optimal ones, is that if you think about that in terms of branch and bound tree, this tree may grow exponentially in size very quickly. And it's possible that if you just explore different trajectories in a branch and bound tree, you may come across nodes from which the solutions on the remaining subproblem could be exactly the same. And that's a point where at least it bothers me a lot to think that we can do better than that. And my dream is that we can do something like this, that we can identify that we're about to explore a subproblem that matches something we have exactly seen before, and that we can, instead of doing this again, we just point out at a different part of branch and bound tree and we say, you know what, we have seen all of this before. And this is what David mentioned in the first hour of the school as the symmetry of the feasible completions. And we're going to talk a lot more about it in this talk today. So, and of course, like as we're talking about decision diagrams here, I do see a big connection here between what we do when we start with a branch and bound tree, and how this can progressively be understood in terms of a decision diagram. Let's say, for example, that we have a very simple tree where we're enumerating, let's say, 6 solutions on 3 binary variables. As you can see, not every completion is possible here. There are 2 nodes where we have a single completion out of them. And here, if you look at every one of these leaves, they correspond to a different feasible solution. But at that point, we don't really care much about representing them distinctively, because they all basically say that you're done. So it would be equivalent to just put all of these nodes together, merge them, in which case we would have a smaller structure, as we're seeing here in the center now. And as you progress to a smaller structure, you can easily detect there are some equivalence classes among the nodes in the other levels of this. I don't want to call it a decision diagram yet, but this is a decision diagram, right? So we know that there are some, you can see here that we have some nodes from which the only completion, the only possible assignment in the next layer corresponds to this continuous arc. And we also see other nodes from which there are 2 possible completions. And what's interesting in both cases is that we can basically reduce the size of this decision diagram by just merging them. And we know for a long time, pretty much since I was 1 year old, that this process can converge to a unique reduced decision diagram upon isomorphism for a given order of the variables, in which each node is going to have a distinct completion set. So what I'm color coding here in the bottom of the diagram, different nodes are nodes for which the completions are different. So, and just for the sake of completeness, I can claim that this terminal node here has an empty completion. And then the nodes above, one of them has a completion corresponding to just assigning 1 possible value. and the other one to assign the two possible values. And it's kind of very simple and powerful structure. And it becomes even more convenient if we assume that in every level of this decision diagram, we're always assigning values to the same variables. For example, if in the first level, we're defining that x1 equals 1 or 0, and conventionally we use a continuous arc for a value of 1, a dashed arc for a value of 0, then the second layer, we could have like x2 equals 1 or x2 equals 0, depending on the type of arc. And the third layer, we could have x3 equals 1 or x3 equals 0. And if we have these subproblems on each level defined on the same variables, it's easier to identify these equivalences. So that's one way in which we're restricting a little bit our representation. So generally in the branch and bound tree, we don't make assumptions about branching on the variables in the same order, but here I'm going to make that assumption so that they can leverage more powerfully what we could potentially do with a decision diagram. And the benefit of analyzing a branch and bound tree this way is that if we're performing a search in that first, if we're exploring this problem in that first search, we are going to have a certain collection of nodes that we have already explored, and we can identify whether an explored node could match one of those. And we're making these two assumptions here. One is that we're going to apply this when we have that first search, and the second one that the order of the variables along every path is always going to be the same. And the problem that we want to answer in each one of these nodes, as we're comparing them, is whether if we have two subproblems on the same variables, which when we're talking about an interlinear programming problem corresponds to the same left-hand sides, but they could have a different right-hand side, whether they're equivalent or not. So as you can see right now on the screen, and this is something that would happen if you always branch on the variables in the same order in an integer programming formulation, which is linear, we have the same left-hand sides. We have 5x1 plus 4x2, and then 6x1 plus 10x2. But the right-hand sides are different. In one case, we have 6 and 15. The other, we have 7 and 11. But in both cases, we have 3 feasible solutions that are the same and 1 infeasible solution, which is the same. So what we want to understand here is whether we can compare these two subproblems and tell that they're going to have exactly the same solutions if we know the solution for at least one of them, or at most one of them, actually. So if the right-hand sides were the same, that's easy to do. What we're interested in is whether we can make that more general, and to what extent can we do that. So there was some knowledge about how to do that for a long time, especially for the case of a single inequality. So if you give me a formulation like this, just a single inequality, let's say knapsack constraint, where you have these variables x1 to xn with coefficients corresponding associated with each one of them, and the right-hand side of, let's say, rho. And we assume that the right-hand side and all these other coefficients, these a coefficients, are all integer. Then we know exactly when these problems are going to be equivalent or not. So this was explored in the case of x being binary, and also in the case of x being discrete. And what I'm going to show next here is the general approach by Abiu and Stoke in 2014, which covers all of that at the same time, at once. So a linear inequality is going to have right-hand side intervals that are going to be equivalent. And I'm going to illustrate this here by these consecutive intervals that you see in front of you. So one of them is going to correspond to all values that would map to an infeasible solution set. So for example, if you talk about 5x1 plus 4x2, and x1 and x2 are binary variables, for any value up to -1, including -1, this is infeasible. Like, we're not going to have any combination of x1 being 0 or 1 and x2 being 0 or 1 that could be feasible given a right-hand side of that value. But now if we make the right-hand side a little larger, let's say between 0 and 3, including both ends, then suddenly we have one feasible solution. And as we push these right-hand side values higher and higher, we're going to have more and more solutions. So we're going to have a sequence of consecutive intervals that are going to have a larger set of solutions encompassing all the previous solutions as well. So if we move this a little bit, we're going to say that for a right-hand side of 4, we have exactly 2 solutions. Then for a right-hand side between 5 and 8, we're going to have 3 solutions. And for a right-hand side of 9 or more, all the 4 possible solutions are going to be feasible. And now the way that we can calculate these intervals of feasibility, once we have explored a subproblem that has these particular solutions, is in a bottom-up fashion, in the same way that when we're exploring, when we're reducing a decision diagram, we work on a bottom-up fashion by merging the nodes together. So let's say that we are in a node V, and this problem is defined in variables x1 to xn. So here we have a linear inequality, right-hand side of row. And then let's say that we're branching on different possible values for this variable xi, I'm sorry. And in one of them, we set xi to be equals to j. What happens in that case is that we're going to produce a new node, vj, where we have a subproblem defined only on the variables xi plus 1 all the way to xn. And one of the differences here is that depending on the assignment that we make, we're going to have a change in the right-hand side value. So all the subproblems in this new level, they're going to be slightly different, even if coming out of the same node, as you would expect, for example, in a branch and bound tree. And let's say now, for the sake of induction, that we know exactly what would be the interval of right-hand side values that would be equivalent to what we find here. Let's say we have a beta j and a gamma j. If we know that for all the children of this node V, then we can calculate the beta and the gamma of the node V by this maximum and minimum expressions that I'm showing here. And as I told you, this is assuming that there's an induction. The base case here is going to be terminal nodes that we're going to treat as a terminal node where all the feasible solutions converge, where the interval is from 0 to plus infinity, and another node where we direct all the solutions that are not feasible. Sometimes we do have a representation of decision diagram in which you have 2 terminal nodes. In that case, it would be any value, integer value of -1 or less than that. Now, what's interesting and important for us here is the meaning of these 2 values that we're calculating. Beta here is going to be the smallest integer right-hand side value that will have the same solutions on that linear inequality on the binary variables. And gamma, as calculated here, is the largest integer right-hand side with the same solutions. So we're trying to calculate which are the right-hand sides that will provide the same solutions that we just got, so that later, if we find another subproblem on the same variables with such a right-hand side, because the left-hand sides are all the same, we can just say that they're equivalent, and we avoid exploring the same subproblem again. Now, at this point, I am done explaining prior work in this topic. Do you have questions about that? Okay, we're good. So we're moving on. So we're going to talk now about the first. Go ahead. Wasn't?
Yeah. So you're trying to understand that which new problems in future would be equivalent to your problem right now, right? Some concept like this.
And I'm not assuming anything about that. I'm not assuming that it's a knapsack or anything. So I cannot leverage any special knowledge of that. I'm just assuming like a problem with linear constraints in general. Makes sense?
Yeah, okay, thank you. Yeah, I was thinking exactly on something like knapsack, so that's why this happened. Yeah, okay.
Yeah, I'm trying to be agnostic with respect to the problem here. That causes me a lot of trouble because if you're trying to be more general, yeah, everything gets harder, right?
Exactly, yeah. Okay, thank you.
You're welcome. More questions, folks? This is a good point to ask any question about what happened so far. Okay, so let's move on to the first contribution of this presentation, which is how can we expand the scope of the single inequality case that I just described to you? So there are a few things, and I mean, I think this is really minor. I think like all the credit here is due to the work that was done before me. From the moment I understood what I did, it's a very small step to just extend it a little bit in the way that we did. So the first thing to notice here is that these right-hand side values, they don't have to be integer. Although there is this assumption in prior work, this assumption can be easily broken, and you can apply exactly the same techniques as before. So what I have showed to you so far is that we have like these closed intervals of feasible right-hand side values, except of course, when all the solutions are feasible or no solution is feasible. In that case, we have like a half closed interval because we have minus infinity and plus infinity. Now, what we have here can be equivalently described in terms of only the betas. So if I'm telling you that, let's say from beta 1 to gamma 1, I have a certain set of feasible solutions. And if I have any integer value greater than gamma 1, I will have more feasible solutions. Then I know automatically that beta 2 is going to be gamma 1 plus 1. So why not just expand this interval all the way to right before beta 2? So if we have, let's say, if this was an interval between 1 and 3, and then beta 2 would be 4, and let's say gamma 2 is 7. Why not say that the interval of equivalent right-hand side values goes from 1 all the way to 4, but 4 not included? Because if the variables have integer values, if the left-hand side coefficients are all integer, then any fractional right-hand side is not going to matter for us. So we're basically expanding a little bit the scope. And now, one interesting thing is that we're no longer calculating two different quantities. We don't have like this beta and this gamma. We just have these beta values. That's going to be very convenient going forward. But in other words, we're basically calculating what's the smallest right-hand side value that would produce the solutions we have right now, and what is the smallest right-hand side value that would produce strictly more solutions than we have right now, which turns out to be the one roadblock from like generalizing this in prior work was this assumption of having like a largest right-hand side with the same solutions. So, okay, that's the first change. The second change now is that the left-hand side coefficients don't have to be integer either. They had to be integer when we were interested in the largest integer right-hand side value. From the moment that we're only interested in the smallest right-hand side value beta, and what's the next beta for which we would have more solutions, we can apply the same logic as described before, and there's no requirement on integrality anymore. And from here, it's a single step to realize that actually, if we have like discrete, if we have discrete variables, no matter like what the domain, we can as well just transform each one of these terms into a function on each variable. So our left-hand side can be an additively separable function, where these functions can look like anything, because if they're independently applied to each one of the variables, and the variables have discrete domains, we can still calculate these right-hand sides the same way. It's only if we had something nonlinear here, two variables being combined in some way that's not straightforward, which would break the assumption that all the left-hand sides are the same, that would have some other issues. So those are all small modifications. I don't think it's worth expanding a lot here, even though, especially because I'm actually just going to assume fractional coefficients. I'm not going to get into an additively separable function. But what's more interesting, in my opinion, is what comes next, which is what can we do if we have multiple inequalities, which is what happens in practice. We're rarely solving a problem where we have one constraint, and that's it. We have lots of constraints, and we have to put them together. And even if they're simple and linear constraints, that makes this problem of identifying equivalence of problems a lot more difficult. So here are some limitations that we have to acknowledge, first of all. So if for each one of these constraints that we want to analyze, we can associate an interval for which, if we just move the values around there, we have the same feasible solutions. Let's say, for example, here we have that same example again. 5x1 plus 4x2 is smaller than or equal to 7. We know that the right-hand side here could be anything from 7 all the way to 9, but not including 9. Second constraint, 6x1 plus 10x2 is smaller than or equal to 11. The right-hand side here could be anything from 10 all the way to 16, but not including 16. Because if we move these two inequalities, these two constraints with this particular right-hand side values, we're still preserving three feasible solutions and separating the solution which is in gray here, where x1 and x2 are both 1. So one thing that you could immediately guess is that, okay, so an intersection of these two intervals is valid. So if the first inequality is between 6 and 5 and 9, 9 not included, and the second one is between 10 and 16, 16 not included, then we have an equivalence subproblem. Well, that is true, but the problem is that doesn't encompass everything that could happen. Let's say that we relax the first constraint. The first constraint can be anything from 5 to 9. But if we make it 9 or larger, but we keep the second constraint between 10 and 16, 16 not included, then the second constraint is separating that fourth solution. So it doesn't matter if the first constraint is allowing that solution to be feasible. If the second one is not, we're going to remain having three feasible solutions. Likewise, if we fix the first one, the opposite of what I just said. Let's say if we fix the second constraint, but we move the first one, again, we can potentially have four feasible solutions for one constraint, but the intersection of them is going to have the smallest amount of solutions. So we're going to still have three solutions. So if we want to talk about all the equivalent right-hand side values, it's not only the intersection of two intervals, but we have to account for the fact that like one of the intervals can be relaxed, if it can be like extended indefinitely, if the other one remains where it is. So one constraint can be relaxed if the other stays where it is. Just to put this in one numerical example to make sure that everyone can follow. So I know right now that I can just put an 8 here and a 15, and I have the same solutions. Now, if I put a 17 here, I'm still okay. I'm still good as long as the first constraint doesn't change much. But if I make the first constraint 9, the right-hand side of 9, now I have everything being feasible. But I could fix that in turn by cutting the second constraint to be a value, let's say 12. So if one of them is separating the additional solution, that's all that matters. It doesn't matter if the other one is separating or not. So that's one thing that's going to complicate things a little bit here. The second one is that these intervals are not independent. Let's suppose that we are okay saying that, okay, let's calculate interval for each constraint, look at intersection. We know that we're going to miss stuff, but we don't care. It's good if it stays more or less where it is right now. All right, so if we just use the methods that I told you before to calculate those intervals, given the feasible solutions that we have, but let's say that one of the inequalities separates three solutions. One of the inequalities makes only two solutions feasible, and another inequality, the one in gray, could potentially make three solutions feasible. So there's this one red solution in the limbo here, which is not exactly feasible for the problem because it doesn't satisfy both constraints. So this is what happens with the intervals. So if calculated in the way that you would with a single inequality, we would actually not get valid intervals because, for example, when we look at the second constraint, we're obtaining like the second end of this interval is actually going to be a value that is already included there. So, but even though we have these issues with like the intersection of the intervals and the fact that one constraint affects what the other constraint can do, there is something else that always remains true, which is if we just make each one of these constraints as tight as we can, which in this case would be, we just make the right-hand side so small that there is one solution being satisfied at equality. Basically, like each one of these constraints is touching one of the solutions. Then that we're going to achieve like a unique right-hand side value. So no matter which values you have in the right-hand sides, if you explore the problem, you know exactly what's the smallest value that you need for each one of the right-hand sides, so that nothing here is separated. So these values here are going to be unique. If we move below 5, we're going to cut one solution. If we move below 10, we're going to cut another solution. And this is going to be very convenient for us. And it's going to be in this way. Let's say now that we have two nodes, V bar and V double bar. They're explored nodes and they're distinct, which means that they have different solution sets. And they have this tightest right-hand side, beta bar and beta double bar. So this right-hand side here is what we obtain by calculating what's the smallest right-hand side value that would produce the same solutions. If you have all the solutions generated, you can always find these values. The problem is you never know them in advance. Now, let's say that we have these two nodes and we want to know if they match some problem that we're about to see. So let's say that we have an explored node U with a right-hand side of rho. Okay, so we want to check whether U can match, can be identical to V bar or to V double bar. So there's some criteria here. There's a necessary condition first. So the right-hand side rho here should be greater than or equal to either of these beta values, so that we know that at least all the solutions of each one of these nodes, explored nodes, is also a feasible solution for the unexplored node in front of us. So that's a necessary and intuitive condition. But then let's say that when we look at these two explored nodes for which we find a match, we see that in one of the elements of the right-hand side of one of them, we have a strictly larger value than the other one. So let's say beta double bar I is greater than beta bar I. What that's going to imply is that there is at least one solution in V double bar for the node V double bar that's not contained in V bar. So if that's the case, and we know that U has at least as many solutions as V double bar, so it cannot, okay, let me just illustrate this to make it easier. So we're looking at what's the set of solutions of U, SU, and with the necessary condition, we're concluding that the solution set of U is a superset of V bar and V double bar. But from the moment that we see that V double bar has some solution that V bar doesn't have, it means that the set of solutions of node U can no longer be equivalent to V bar because there's at least something else there. And now the interesting thing is, if each one of these explored nodes has a different set of solutions, so these right-hand side values are not going to match in all the values, then either we're going to see at some point for every pair that matches the necessary condition for an explored node, one of them is going to eliminate the other one. So, and this is a very curious fact. What that means at the end of the day is that if you do that first search, and you keep track of what's the tightest right-hand side value for each subproblem that would give you the same solutions, then by looking back at them before branching on any new node on your branch and bound tree, you can tell whether there's one subproblem we have seen before that could match the current one, or you could tell whether there is none. So you're never going to have more than one node being potentially equivalent to the one that you're about to explore. So it really comes down to whether these two nodes match or not. Now, that creates those are necessary conditions, but they're not sufficient. In order to guarantee that this match is sufficient, what you can do is just pre-populate the set of right-hand side values to make sure that at least you have at least one vector corresponding to the tightest right-hand side values, including each possible solution on the remaining variables. Now, this is not very efficient, but this was the only sufficient condition that we could establish that could help us make sure that these potentially equivalent nodes are indeed equivalent or not. And because we have to generate all of these nodes ahead of time in a bottom-up fashion to make sure that there is equivalence, we can only do this for the last layers of the decision diagram, which in any case is where most of these symmetries are going to be detected and where we can have more potential to merge nodes. So these are the results that we got with, depending on the number of layers that we use for this bottom-up pre-processing. So as you can see, the more layers that we try, in which we apply this technique of identifying the subproblems, the fewer branches we generate to enumerate all the solutions. And this is for a set of problems from the MIPLE benchmark. And we also reduce the runtime. We don't reduce the runtime as much as we reduce the number of branches, because of course there's some extra pre-processing here that's required, which is the part that I don't like so much about this work. And here I'm just going to summarize the contributions of this first part of the talk. So in the case of a single inequality, we extended the existing approach. So it works now for any left-hand side that's additively separable and any fractional right-hand side. In the case of multiple inequalities, we show that there are limitations to applying exactly the same method. We show that there is a necessary condition that can be used to tell whether two nodes can be equivalent or not, an explored node and a node that you haven't explored yet. And that you can use an elimination procedure to discard all but one of the explored nodes as potentially equivalent to an unexplored node. So you can remove most of the possible matches, and you come down to a problem of, okay, here is a problem that I'm going to explore, and here's the only other here's the only subproblem from the past that could potentially be equivalent to this one. And finally, we have a sufficient condition to make sure that these two match. And what I want to say again, if it wasn't clear so far, I definitely don't like the sufficient condition. It's overwhelming. It imposes a huge overhead in terms of preprocessing. And if you're looking for some interesting thing to do in this area, if you find that like identifying equivalence subproblems is something you would like to explore, finding a better sufficient condition here is, I mean, I would be so excited to hear anyone finding something better than what I did, because I don't think what I found was very good. Well, with that, we conclude the first half of the talk. Do you want to ask questions now? Looks like we're good.
Thiago, I actually have a, sorry, we have a question for someone.
Okay.
I will just keep quiet. Someone else ask the question.
Mostly, go ahead. Go ahead, Mostly.
Oh, it's me. Okay, okay. Thank you. I thought someone else. So, is this applicable? You said for the time that we have multiple inequalities, is it okay if all the right-hand sides are the same? Have you tried it?
So if you're right, I mean,
like a binary problem, I mean, decision variables are binary, and your right-hand side, all of them are ones.
Set packing, for example.
Yeah.
So from the moment
exactly.
you start, but from the moment you start assigning values to these variables, the right-hand side is going to change, right?
Okay. The right-hand sides would change. We want to satisfy all these constraints, right?
So let's say you have something like this. You have like x1 plus x2 plus x3 smaller than or equal to 1, right? Let's say we have a bunch of this, maybe with different variables here, right?
Yes, that's covering.
So let's say if we have like x1 equals 0, then we have a subproblem similar to that one, but like only on like with the right-hand side of 1 again, right? If we have x1 equals 1, then that right-hand side is going to change, right? It's going to be x2 plus x3 is smaller than or equal to 0. Oops. But I see your point that like if you have a very well behaved constraint, like set covering constraint, what you really care about is whether the constraint is satisfied or not, right? By the previous assignments.
Okay.
Is that what you mean?
I just wanted to see whether you checked, is this method applicable for this problems or not? so that maybe we can find some connection to, I don't know, using, if we can find the link between your method and decision diagrams, straight connection between them, not to, so you are partitioning your space, if we can do it in another way or not. That's just one thing that I wanted to see if you have checked them or not.
Okay, so I mean, what we have here would be applicable to any formulation like that. But of course, like if you have a formulation that's more specific, there is always something, you can always leverage a few more things, right?
Okay.
And for example, in the other paper that I'm going to describe, even though we don't talk much in these slides, one thing that we did was we identified inequalities that would be satisfied by any assignment from that point on. That's actually like a cheap thing to do. If you can just tell that, okay, at this point, the right-hand side is so large based on previous assignments that any assignment to the remaining values, to the remaining variables, is going to be feasible. So like if you want to match if you want to match sub-problems based on the right-hand side without considering intervals or anything, it's a very simple comparison. But you know that some of them are large enough, you can just ignore the exact value and just say, okay, like this particular inequality, I don't care anymore because the value is larger than a threshold. That's something that made a big difference in the other paper.
Okay. Yeah, I'm sorry to compliment you, but I believe that the problem for the set packing like this is well defined, because it's essentially what are the items that you can still put in your set packing. So then you have exactly the complete equivalence class. So you don't need to do all that, the different thresholds that Thiago is doing. You can use the decision diagram that we used, regardless if you have a different variable ordering. If you have two branching nodes, you mark the set of visited nodes that you have visited, sorry, the set of eligible vertices that you have. So then you know exactly when you're going to have the same type of branching in the two regions.
Okay. Thank you.
Yes. Yeah, as I said before, like I always try to make these things more general, and which means that I also put myself in trouble because I want to ignore these things. But yeah, what Andrea said is right. Like if you have more information about a problem, you would never default to a general method, right?
I have a very quick question. Sorry to bug you. So here you're not considering the objective, right? As one of the, you're just considering the feasibility system. If I have an upper bound on the objective in this case, for example, you can define that the objective function, you have a linear inequality less than or equal to that upper bound, and incorporate that into your system. That makes sense for you to see not only that they have the feasible space, but also if they have the same, if you won't be able to improve the objective function value. Is there something that can be done in that aspect?
Oh, it feels like you're trying to sell my paper for me. this connection, what comes next, but that's something I thought a lot when I was working on this. And one of my concerns was, if you put a bound on the objective function, that's another constraint.
Right.
So if you're thinking about exactly representing the near optimal set, that may actually make it more complicated to represent.
Okay.
But if we are okay with a relaxation, then that actually can be a good idea. I mean, like you can have a decision diagram where you can take into account you can take into account a bound on an objective function, and at the same time make the decision diagram smaller by other means, which fits perfectly with what I'm going to do now. So, oops. As soon as I stop annotating here, so I can move on to the next slide. So if we assign, I'm just going to make this slide here just to make sure that this is mentioned before I talk about it, but you have seen this in the previous talks. If we associate costs with each assignment and without loss of generality, we can just assign them. If you're thinking about the 0-1 problem, you just have to assign costs to the 1 arcs, because the 0-1s can be considered 0 as well. Let's say that we can solve if we do that, we can solve optimization problems over the decision diagram. Let's say, for example, that the arcs coming in, the one arcs for the first variable have a cost of 1, for the second variable have a cost of 2, and for the third variable have a cost of -3. Then the longest path in this decision diagram is going to be an optimal given by this particular path here. Whereas the shortest path is the optimal solution for the minimization problem, and it's going to be given by another path over the decision diagram. And the fact that you can extract optimal solutions for minimization or maximization using a decision diagram is very convenient. Now, just to cut one concern from your minds right now, usually we talk a lot about shortest paths, but we don't often talk about longest paths because in general they're hard. But a decision diagram is a direct acyclic efficiently solve a longest path problem, which is not true in a case where you can have like a more general graphical structure. Now, here's another idea that came from Hadzik and Hooker and was one of the things I worked on my PhD. Let's say that we want to represent all the solutions, all the near optimal solutions of a problem. Here's an example where we have an optimal solution of value 3, and we want to represent any solution with a value between 3 and 6. So here you can see on the left the weights I'm associating with one arcs, so 3, 2, and 3. So and we have 3 different solutions here, ranging value from 3 to 6. And here is a smaller decision diagram where instead of 3 solutions, we have 4. But the 4th solution is a very expensive one. It has a cost of 8. So since we know that we have a decision diagram to represent only solutions with costs ranging from 3 to 6, if we ever come across this particular solution, we're going to ignore it because it's too expensive. But the benefit of adding more solutions to decision diagrams sometimes is that this allows the decision diagrams to become smaller, which is what we were working on here. We were thinking about how can you come up with a relaxation that's going to make it easier to represent all the near optimal solutions of a problem in a way that you're not going to get trapped into identifying false solutions. So since we can efficiently compute the value of any path in a decision diagram and whether we can extend a particular path to obtain a solution of a given value, that's something that we can easily do. So what happens in this sound decision diagram, and the reason why we find this is a good idea is that we maintain this correspondence between the near optimal paths and solutions of the original problem. And the extra solutions that we would include in this diagram are there only to shrink the diagram as much as possible. And we can avoid the solutions by fixing variables from either decision diagram. If I start fixing, let's say, variable x1, x2, and x3, I know what was the cost incurred so far. I can calculate what's the shortest path towards the terminal, which would tell me what's the cheapest solution, what's the solution of the smallest cost that would include that particular prefix that I have fixed so far. If that goes beyond the near optimal threshold, then I know that the solution that I'm trying to construct is not feasible, or at least it's not relevant for the current purpose. And one interesting thing is that these decision diagrams can naturally arise if we merge nodes in a top-down construction. So let's say that we're looking for all the near optimal solutions of a problem where the optimal value is 7, and we're looking for a delta of 1. So interested in solutions between 7 and 8. Let's say that from the root, we go to this one node in the middle for 2 different paths. In one path, we have a value of 5. In another path, we have a value of 6. And we identify that they're equivalent either because of right-hand side or because this is a particular problem with a specific structure where we can tell that the solutions are going to be the same from that point on. But remember, we're only interested in the near optimal ones. So from this point on, let's say that we can have 2 other paths that could reach the terminal, one with a cost of 2 and one with a cost of 3. So if we take the 2 orange subpaths, you have an optimal solution. If we mix orange and yellow, you have a near optimal solution, value 8, and we want to count it. But if you only take the yellow subpaths, you have a solution of value 9, which is far more than what we're interested in, But if we don't represent the solution, we would have to split this node in two so that we would have three solutions being represented instead of four. And so this is a feature that we actually came across as a bug when we were implementing the code, but it was a very convenient one. And so starting from that, we began to analyze how can we create diagrams that are what we call sound compressed. So we're going to start with a diagram representing near optimal solutions and figure a way to make this diagram as small as possible while not introducing any solutions that would be in the near optimal set. And here's one possible example. So in this decision diagram here, we have solutions ranging value from 1 all the way to 7. So the optimal value is 1, and the delta here between the optimal solution and the threshold of the near optimal is 6. So if we look at this particular combination here, we have node U1 and node V1. The shortest path from the root to node U1 has a cost of 5. And if we compare U1 and V1, V1 has one completion that differs from U1, which is this one in orange. If you look at the other one, consisting of the two orange arcs followed by the black dashed arc, that's exactly what you can do from U1. But this extra completion here has a cost of 3. So if we were to put these two nodes together, this in such a way that from U1 you could take this orange path, we would have a cost of 8, which therefore would exceed the near optimal threshold, and it wouldn't matter for us. So if we do this operation, we get rid of 2 nodes and 2 arcs of the decision diagram, which seems very convenient in this case. And this is a process that can be applied in the same way that you do the reduction of the decision diagram to find the smallest structure. And this process is going to converge to a sound decision diagram of minimum size. But what's curious about this process is that we may obtain different decision diagrams of minimum size. So in this example here, let's say we have this node U3, and we want to remove this node. One possibility is to merge it with the node Q, and the other possibility is to merge it with node V3 on the other side. Both of these operations would produce what we call sound reduced decision diagram. So it's a sound decision diagram where all the near optimal solutions are the same as before. Any other extra solutions introduced by merging nodes are not near optimal, and there's nothing else we can do. It's of minimum size. So it's a curious process which can lead us to distinct compact representations of a near optimal set. And we were very excited about this. And one thing we started wondering is whether we can also generalize this idea and talk about, okay, I'm interested in solutions in this range of values between the optimal and the optimal plus delta. What if I also introduce solutions that are better than the optimal? And here's something that you should never talk in an optimization talk, better than optimal. But basically, like we're talking about infeasible solutions, but solutions that because they're so cheap, you could tell that they cannot be feasible. So we thought about that, and we came across a very frustrating result, which is it's easy to which is that if we were able to do that, we could in fact solve any NP complete problem. So like telling whether you can extend a solution, a path in a decision diagram to be in a particular range of values when you consider the costs of all the arcs is as hard as a zero subset sum problem. So yeah, that was a big no. And that's something that's easy in a sound decision diagram. If you're only thinking about one of the extremes, in a minimization problem, you're excluding larger values. In a maximization problem, you're excluding smaller values. That's totally fine. So here we have some comparison between the size of the sound reduced decision diagrams as these red bars, and in blue we have the size of the corresponding trees enumerating the same solutions on a number of different manipulative problems. And as you can see here by the log scale, this difference is quite large. And one other thing that's very interesting here is what happens as we include more and more solutions in this set. So, okay, we got it. Sorry. So David.
That was me. Yeah. Are these nodes in this y-axis?
Yes, these are
Okay.
nodes.
Just wondering. Thank you.
Sorry, yes, I forgot to mention that. So here what we have as well is the number of nodes in the case that you represent all the solutions up to a certain near optimal gap of this problem P0040 using a tree as the dashed line. Then in this line with the triangles, we have a reduced decision diagram. The decision diagram, a reduced decision diagram is definitely going to be smaller than a tree. And you can see here that's orders of magnitude small. Now, one of the curious things about decision diagrams is that sometimes they get larger in size, sometimes they get smaller in size. And what we see here as the size of the reduced decision diagram goes down is that as we're including more solutions, we're identifying more completion symmetries, which are allowing us to make the representation smaller. And the other curious thing that you can observe here is that when we look at the sound reduced decision diagram, the decision diagram with the near optimal solutions, plus hopefully a few more solutions, what happens is that the size of this diagram is never going to go down as we increase the near optimal gap. It's monotonically non-decreasing. And in the worst case, this is going to be as large as the smallest decision diagram representing all the solutions. So it's an interesting property worth exploring more. And this is what we have seen whenever we're able to enumerate all the solutions. So in this case here, when we get to this near optimal gap of 7,000, we're enumerating all the solutions of the problem. And here on the right, we have another type of problem where we can't get anywhere near to enumerating all the solutions of the problem as you're increasing the near optimal gap. And as you can see in this case, we have a very different regime. Basically, the size of the tree, the size of the reduced decision diagram, and the size of the sound reduced decision diagram, they all seem to grow exponentially on the depth, but they're in different orders of magnitude, which is what's very interesting for us here. But the most relevant thing about this whole idea of having a sound decision diagrams is what you can do if your objective function changes slightly, so that your optimal solution will be within the near optimal solutions that we had before. So if we have very relatively small cost perturbations, the sound decision diagram are going to still contain the optimal solution because we're preserving all the near optimal solutions. And experiments with 39 problems from the MIPLib, we did re-optimization on top of the sound decision diagram, as opposed to using Cplex to solve the problem from scratch. And what we observed is that the time to re-optimize using the decision diagram, as opposed to resolving the problem with the perturbed coefficients, is a lot smaller. It varies depending on the problem, but in many cases, it's order of magnitude smaller, which is very convenient. So in the case of post-optimality analysis, our contributions here were the following. We showed that this minimum size sound decision diagram may not be unique. So the sound decision diagrams existed already, but we made a formal treatment of them, and we understood how far can we go with them in terms of reducing the size of the representation. And even like a natural process such as merging nodes of subproblems that have the same right-hand sides, therefore just including some extra feasible solutions can naturally yield a sound decision diagram if this means that we're including solutions that are not near optimal anymore. And we define this operation called sound reduction that can be efficiently used to compress a decision diagram to a minimum size. So this is going to be efficient on the size of the decision diagram. The decision diagram itself, of course, can be very large, or just producing the decision diagram can be a very expensive process based on like if you're enumerating solutions of an NP-hard problem. And we also observed that the generalization of sound decision diagrams for a range of values is going to be computationally hard. And well, we were able to construct very concise representations of the solution pool. And most importantly, with this concise representation, re-optimizing over the sound decision diagram is a lot faster than calling a mathematical optimization solver from scratch again. So with that said, here are some of the main references. So some of the classic papers, especially like preliminary work leading to what we did. And at the bottom, you can see the two papers that I described here. The paper with Professor Hooker and the other paper that I worked on my own after finishing the PhD. And with that said, thank you very much for your time.
Thank you so much, Thiago. Do we still have any questions? Fantastic. Okay, so if you don't have any questions, we are almost done for the day here. Actually, we are done for the day. I hope to see you all tomorrow. We're going to have now excellent talks in different fields. I believe tomorrow we're going to have a talk by Quentin on how to improve bounds using machine learning. And then we're also going to see more about on the stochastic optimization aspects, high-level optimization, and many other applications that I hope that can be helpful. Also, interactions between decision diagrams and column generation, right? Because you can think that the paths of the diagrams are actually columns in some of the routing applications that you can use that for. And that's excellent. And we still have a long way to go, but I hope that has been helpful. I hope today was a great. Thank you so much, Thiago. And I hope to see you all tomorrow. All right.
Thank you very much. See you tomorrow.
Thank you. See you tomorrow.
Thank you.
Bye-bye, everybody. Hope you have an awesome day.